recording. So yeah, before we get into, well, today we're going to talk about arc fault, ground fault, overcurrent protection, and stuff like that. But yeah, let's review we'll review that electric sheet. And there's a couple of ways you can submit that thing. I mean, if you go in the original assignment and you click write submission, it'll allow you to type in, like, so you could go through and type
Okay. Okay.
each one, you know what I'm saying?
Okay.
So if you were to pick, like in this case, you can all see the screen, I hope, and just say like 1 is this and 2 is this and so on. Really though, I mean, that would be to show me all of your answers. So, and they're all numbered, so you'd be able to go through, and I know it's a pain in the butt. I agree with you sitting
So
there.
this is just like an example, right?
Sure. No, this is the actual, this is a real deal. This is a finished version. I'm not gonna go over it real heavy. But yeah, square footage right from the get-go is the most important, right? I mean, not most important, but, and that's because of our formula here, where we figure out what our general lighting is by the square footage multiplied by 3, right? So that gives us a number here. And based on that number is what our calculations in the next couple of steps are. So we figure out how many lighting circuits we have, right? Because in this case, we came up with like 5.39. Yours might be a little different. Like I say, it depends on what you come up with as the square footage. But if you round up, so 5.39, we say, okay, we're going to have 6 circuits. So that means I'm going to have 6 different circuit breakers in the panel just for this, right? So there's going to be 6 15 amp breakers in there for this purpose. And then you go through and based on NEC, what required to have as a minimum requirement. So in this case, I have to have 2 branch circuits for this, right, for small appliance loads. I have to have 1 for the laundry branch. And so as you can see, this is a minimum. So you go to 2 and then it's multiplied by this 1500. So we get a solid number there. We get our solid number here from the 1. And then all this one is adding all these together. So we come up with like an overall, right? Excuse me. So we get this number here. And then, and remember now, on page 4 of this has this instructions for like each step, kind of, you know, to help you out with any of the math and formulas and stuff like that. So each one of these, you're just going through and plugging in the formulas, adding them, subtracting them as you need to. And you're coming through and sizing each one, right? So, I mean, and of course, you can't put stuff in there that isn't in the house, right? So in this case, there wasn't a sump pump listed and stuff like that. So, but wherever there is stuff listed, that's what you're going to do is come up with like all these appliances all together and come up with an overall appliance thing. So what we're trying to do is figure out, okay, how much supply is my house going to want? And by figuring all these out and come up to here, and of course, we have the motor factor involved. That's like, what's our overall continuous duty going to be on this and that type of thing. So that way we come down to this guy, number 34, tells me what size service I'm going to need. Okay, and remember, we're at 100, 150, and a 200. So in this case, if I look at it even, so if you're in this ballpark, then you're pretty much on track. And you're going to tell me that, well, we're going to need a 200 amp service. But now based on this, tells me wire sizes, right? So if we looked it up, we would see that in this case, it would be a 2-aught or 3-aught AWG, which is, and as far as wire sizes are going, these are pretty freaking big. But this is what we're required to have based on the amount of current we're going to have in our service. And then you go through and do some more calculations on this until we come down to this one. And I consider this one to be important too, right? What size neutral conductor are we going to have in this house? And you're going to tell me that wire size. And that's important, right? because we're going to install this, we're going to buy this stuff, and we're going to put it in place based on what you calculated. And then we get down to the bottom ones here, and these are important as well. And what's this? The grounding electrode conductor. So that means what wire size we're going to run as our main ground, you know, because we got that copper rail spike we're going to pound in outside somewhere, and we're going to run a wire in to the cabinet. So, you know, what size we're going to need there. And then when we look at the final one, what's our raceway size? And the raceway is going to be what? Like what size pipe we're going to have going up on the mast and stuff and coming down to handle this big gigantic 2-aught, 3-aught going through, this number 3 and this number 4. So, and that's what I mean, and really the bottom line is getting into it, and right, and what's this going to do is basically this sets us up, we're going to size everything outside based on our calculations, what size wire we're going to need, what size pipe we're going to need. So we're going to buy, of course, a meter box. We'll have the meter socket in, but our mast size is going to be based on what you have here. And the wire size going up through that out to, you know, where Ameren or ComEd or whoever's going to hook up to, it's going to be based on that. And then coming through from the meter box into our service panel. And what size service panel we're going to buy. So in this case, we need a 200 amp service panel, right, with a 200 amp main breaker on it. And so this is all like what you're beginning or what equipment we're going to have to put this service in. And then we'll be able to size through, and based on this, how many breakers are we going to need, right? How many branch circuits we're going to have installed and all that. So pretty much what this will do is you'd be able to set up and buy all your stuff for your service entrance, getting all your circuit breakers, you know, purchased at this point and stuff like that. So what this does is, I mean, you'd be able to basically come through and make a materials list out of this. So then you figure out, and of course you'd have to do some more calculating and whatnot. And it's like, okay, how much wire am I going to need throughout the house? And then you'd be able to kind of go through each room, see the square footage involved and so on. And pretty much you could come up with, based on all your calculations, if they're done right, you'd be able to come up and figure out pretty much what your whole materials list is going to be. And then, of course, what's the only other thing you have to add in on that would be labor. So if you got parts and labor, now you've got everything you need to basically make a job bid on these set of plans that you got. But those are the ones I consider the most important, the ones in red. I mean, all of these are important, right? Being able to size these things the proper way based on the information that has on the plans, what sizes they're going to be, multiplied out, you know, any service factors involved and that kind of thing. So we come up with bottom lines and then just keep plugging away. And basically that's really all it is, you know, start here. It's like, we got this, and then all this information comes out of the plans themselves, right? What size the water heater is, the dishwasher, and all that stuff. Yeah, and that's pretty much what I'm looking for. And like I say, if you're off, you know, like I said, if your square footage isn't dead on, but your calculations are all right, that's what I'm looking for. So based on everything that you give me, and then you tell me what size stuff you need for your house that you're gonna do the electrical for. Does that help with that? I think giving you a good idea. All right, and that's really what we're looking for. I mean, I want you guys to sweat it a little bit, you know, because this is a biggie, and this is why we jumped ahead in the chapters to give you, you know, time to work on these different ones and stuff like that, just to get a good idea of everything. But really, this is everything you would need, like right from the get-go. And once you get your service entrance installed, I mean, you now have power delivered to your house. So now it's just a matter of you going through and doing all the individual branches, right? And get your wiring laid out and get everything pulled through, get your junction boxes and going out and all that kind of stuff, roughing in the house, but that's all part of the, part of the trade part. But, and also, so like I said, we're going to go into, excuse me, ground fault protection, overcurrent protection. And so I got a couple of, I know they're horrible, a couple of videos though, but Eaton did a, oh, what is this?
Electrical fundamentals.
No, sorry. This is the one. I think.
Today we'll be talking about the developments in circuit breaker technology and how they can protect homes from one of the leading causes of household fires. Early residential electrical circuits were typically protected by fuses. When the circuit saw too much current, the metal strip in the fuse would melt apart or blow due to the heat generated. Of course, each time this happened, it had to be replaced. In 1936, Westinghouse unveiled the first residential circuit breakers. These breakers soon became the standard protection in residential wirings, replacing fuses with a more reusable design. Their operation was simple: monitor the circuit for excess current. Today, the same technology is still in use, but with a few improvements to help with better performance and quality. Now, there are two events which the standard thermal magnetic breaker protects against: overloads and short circuits. An overload is where a circuit is pulling too much current and could potentially overheat and damage the wiring. This is often seen where too many devices are plugged into one outlet or on the same circuit. Once the breaker senses this overload, it trips, protecting the circuit from causing damage. It does this by way of an engineered bimetal that bends when current above its rating is applied across the circuit. It would only take a few seconds to trip the breaker if a high amount of excess current is being pulled through the circuit, but it could take several minutes if the current is just above the breaker's rating. Another condition that the standard breaker protects against is a short circuit. This is when the hot conductor comes in contact with the ground or neutral conductor. The resulting short circuit creates a spark or arc that often damages one or both of the circuit components. On a typical 20 amp breaker, a short circuit will increase the amount of electrical current, starting at 10 to 20 times its normal load, and can go as high as the full current rating of the breaker. Protection from short circuits is provided by means of an electromagnet. When current flows through a circuit, there is an induced magnetic field. Under normal conditions, the magnetic strength is not strong enough to mechanically trip the breaker. However, when a large amount of current passes through the circuit, it significantly increases the magnetic strength and will trip or break the circuit within a fraction of a second. In 1964, Westinghouse introduced the ground fault circuit interrupter, or GFCI. Where a standard thermal magnetic breaker is used to only protect the wire from short circuits and overloads, GFCI breakers protect people and equipment from electrical shocks. These breakers include the standard protection of a thermal magnetic breaker, as well as 5 milliamps of ground fault protection for people, or 30 milliamps of ground fault protection for equipment. A ground fault occurs when the current leaks from the hot wire to a grounded path. These leaks, if left undetected, can lead to equipment damage or cause harm to anything or anyone it comes into contact with. The GFCI breaker measures the amount of current leaving on the hot wire and compares it to the current returning on the neutral wire. If there's any difference, it assumes the missing current has leaked onto the ground wire and trips the circuit. GFCIs are required in bathrooms, kitchens, basements, garages, near swimming pools, and outdoor receptacles. The next type of breaker that was developed for residential applications was the arc fault circuit interrupter, or AFCI. Studies done during the early 1990s showed that a significant amount of residential electrical fires were being caused by a phenomenon called high current arcing. These situations occur when the insulation in the hot wire is compromised and the current is given an arcing path to the ground or neutral wire. Now, the device I have here is designed to recreate this high current arcing fault on a circuit monitored by a typical thermomagnetic breaker. If I cut into the lamp cord quickly, it will create a short circuit, which this breaker will obviously detect. But the conditions leading to a high current arc are much more subtle, not nearly as abrupt as a short circuit. This arcing, which can be in excess of 10,000 degrees Fahrenheit, creates only 75 to 125 amps of overcurrent, not nearly enough to trip the 200 amp short circuit protection of a standard thermomagnetic breaker. Additionally, the arc usually doesn't last long enough to heat the bimetal strip, tripping the breaker on thermal overload. As a result, the arcing fault is more often than not completely undetectable by standard breakers. The branch feeder AFCI was launched around 1994 to provide the overload and short circuit protection, plus protection for the high current arcing where the current exceeds 2 to 3 times the breaker's rating. Internal to the AFCI, a current monitoring circuit board detects any anomalies in the current flow and trips the breaker when a current signature matching an arc is detected. So let's try the same test with an AFCI breaker. As we see, the branch feeder AFCI trips under this circumstance. While this AFCI breaker has been providing fire protection for many years, additional studies have found that another type of arcing also contributes to electrical fires. This arcing condition is called low current arcing and is most common in household cords such as extension cords, appliances, lamps, etc. In this situation, the phase or hot wire is broken, but the two severed ends are still close enough for arcing to occur between them, resulting in the arc actually jumping across the gap. Since this arc is in series with the load, the current will be limited by the loads being drawn. This low current arcing is in the 5 to 10 amp range and won't be detected by the branch feeder AFCI. The combo AFCI was developed to detect this low current arcing. In addition to short circuit, overload, and high current arc fault protection, the combo AFCI provides protection for low current arc faults. As we see, the combo AFCI is able to detect this low current arc fault where any other breaker would fail to respond. The challenge with designing the combo AFCI breaker is that every electrical device will create arcs during their operation. When the contacts close or separate, they create these small arcs, just as I was trying in the demo here. The protective device needs to differentiate between these operational or intentional arcs, such as the flipping of a light switch or operation of a motor, and the non-operational or dangerous arc. The combo AFCI breaker is designed to ride through these operational arcs and only look for sustained low current arcing before tripping. Undoubtedly, you can see why arc faults are some of the most overlooked potential hazards in today's homes. But with Eaton, you can have the silent protection of the combo arc fault circuit interrupter, as well as peace of mind that your home is safe from these dangers. For Eaton Corporation, I'm Jason Mitzberg. Thank you for joining us today.
But that's kind of what we're going to be looking at today. We got basically we're looking at chapter 6, which deals with pretty much all overcurrent devices, which these days we have tons and tons of different types. Yeah, you got ground fault circuit interrupters, arc fault circuit interrupters. These days we have surge protectors, immersion detection circuit interrupters, appliance leakage current interrupters. There's pretty much any kind of happenstance that you can think of that could happen. We do have protection against it. A lot of times these aren't installed in homes as a regular thing, partly as price. I mean, it's becoming more often now where you will see AFCIs actually being part of the initial build, and they will be put in the panel. GFCIs have been around quite a while. Arc faults are still fairly new in the whole scheme of things. They've been around since the 90s, but and of course there's surge protection devices. A lot of places, a lot of people use these now for computers and stuff like that, where they have a little surge protector built in that'll trip if something were to happen, that kind of thing. Believe it or not, though, you can buy these actually as receptacle units. You can, and they are different colors depending on their operation and that kind of thing. Arc fault AFCI receptacles are kind of odd looking. They're blue colored, but the reason being that they look at this, I mean, number one, right? There's can be no compromise where human life's involved. I mean, you need to safeguard people from the dangers of the home. Huh?
What's the difference between an AFCI and a GFCI?
The way they work. So the GFCI looks for a certain amount of current, right? But it's a small range, and the premise is being that they want to keep it below the amount that'll tickle your heart, which is about 10 milliamps. So a GFCI is supposed to trip at 6 milliamps. And okay, the difference being in the way they work. So a GFCI is what they call active, right? So it's constantly sensing and it's looking for the differences of current. But now an AFCI does it differently, and that actually has an actual circuit board built into it. Okay, so the circuit board is actively detecting whether or not there's like with that video explained, if there's that ripple going on. And what does this largely protect against? I always like to use the example of its extension cords. Really look at it. You know, you don't know your extension cord's compromised. Let's say, I don't know, somebody in the house ran over one of the extension cords with a vacuum cleaner and it got chewed up and it looked okay. So you just put it back on the ground and let it go, right? But let's say in reality, it ripped it up pretty good. And if you get a break in the insulation and that kind of thing, you can have these like little arc ripples happen, but it's not a big enough current for anything to trip on. So here you got this shock potential just literally sitting there, right? So a GFCI won't see it until something actually happens. But in this case, there's not enough current to go on that anything could happen. So let's say you take that extension cord, right? It's a little twist to it, put it back on the floor, it's on the carpet. So now you've got little dances of electricity going on across this, little arcs happening, right? Because you got both the hot and the neutral here. But it isn't enough to make anything trip on it. But it is enough to have this constant current happening. And so these little flashes can ignite. And so what would happen is basically you'd end up setting your carpet on fire or setting the back of the couch on fire or something like that. And so what an AFCI will do is it looks literally for those little ripples. So if we were to like put in an AFCI breaker and you compare it like size-wise to a normal breaker, you know, the circuit breakers that would be in the panels, the AFCI one's about twice as big, and it has an extra wire to it as well. But because there's a whole, on the bottom half of that circuit breaker, there's a whole circuit board involved that's built into this thing. And so basically your difference is the amount of the way the current occurs, the way they trip. So the AFCI is great for things like extension cords or devices that might be marginally problematic, but nothing to cause like a GFCI to trip. A GFCI is sitting there looking literally for this imbalance of current. And the minute it detects that, it goes, whoop, you're out. Where, and then like the regular, you know, the old standby ones, right? The ones they built back in like the 20s and 30s, the circuit breaker ones, they're literally looking for an amount of current over their rating for a given amount of time. And even though that time's still in seconds, you know, seconds can be lethal as far as like how much electricity it takes to stop your heart or how much electricity it takes to start a fire. So that's one way to look at that. It's like the GFCI is literally looking for that magical range of current imbalance, and it'll trip. Whereas the AFCI is looking for little ripples in current change, and then it'll trip. So it's really a matter of how the electricity is. I mean, it would be probably a good thing if all of your receptacle breakers throughout your panel were AFCI backed up, believe it or not. Like all the ones that you're planning to plug the vacuum cleaner in or any extension cords and that kind of thing. Yeah, and they do make them in both circuit breaker styles and in a receptacle mount. So you could literally have an AFCI receptacle mounted in place in given areas too. It all depends on what kind of protection you're going for and that kind of thing. Does that answer? I hope that
Yeah.
a little bit too far, but but anyway. So yeah, if the equipment's not properly grounded, the potential for electric shock is present. And the shock hazard always exists whenever the user can touch both the equipment and grounded surfaces. And this happens more often than you think. And it could be something silly, like maybe you went in and you touched the toaster with one hand and touched the refrigerator with the other hand, and you get a little tingle or a little zap. That means something's happening there where either A, something's going on with the ground, or B, something's going on with your equipment with the ground, and you're getting some kind of electrical trickle. And this does happen. But this electric shock can cause internal damage. I mean, there can be damage. You don't have to die, right? There can always be different things that happen. Oh, let's go. Anyway, but yeah, it depends on a few different things, like humidity factor, what's your path to ground, your contact duration, you know, how long are you getting electrocuted for or getting shocked for, what your body resistance is, and the circuit characteristics. I mean, the resistance of your body for pretty much everybody. I mean, everybody varies. Everybody's going to be different, all depending. There's so many different things that come into play with resistance, but normally, I mean, you can run anywhere from a few hundred ohms to a couple of thousand ohms of resistance in your body. But you got to remember that's all part of Ohm's law. So if you get hit with a certain amount of voltage and you have a certain amount of resistance, then you're going to have a certain amount of current. But the way they look at it is, if you're usually dealing with volts that are less than 50 volts, you're usually on the safe side of things. And anything over 50 volts is considered potentially lethal. It has the potential to kill you. And you got to watch some of these things, because some of this, like, see if it's at the current range that it's at and how it feels. So 0.4 milliamps can't be felt. 1.1 milliamps is a little tingle. 1.8 is like slightly shocking. You know, really what it comes down to is the point where you're not allowed to let go of the circuit anymore, which is up in this range, right? And that's where you can't, you know, you can't let go. Your muscles cramp up. You're pretty much, you've lost body control and that kind of thing because the electrical stimulus is interfering with your brain synapses and that kind of thing. But so pretty much anything over this point is considered lethal. You can't, so 23 milliamps and up, okay, but here you go, 1,000 milliamps. It's like, okay, yeah, if that's going across your heart, then you're done because it'll stop your heart, and it's all on time base and everything else. But that's how they look at this. So here's a typical graph for a GFI's operation, okay, and you follow this yellow line here is what your maximum allowable is. Here's the red line is what kills you. The yellow line is maximum acceptable. And this bottom, like, I don't know what color that is exactly, but the bottom one here is your usual operation of GFCI's range, how much current it's going to allow through. So as long as you're keeping it below this line here, you're totally acceptable. Because here's where heart stopping happens, is essentially the way to look at this thing. So if we looked at, yeah, the 6 milliamp range, okay, which is way down here, and then we look in time involved. And so as long as we keep that below this time, then everybody should be safe. There's no danger of electrocution and that kind of thing. And that's really what a GFI is looking at. So it's going to follow through, and at a given current imbalance, it'll open up, and it's usually very quick. And you notice that, see, and the AFCI is still relatively new, so there is no, like, we're required to go through and install GFCIs when we have rules involved for that. So all bathroom, basically the rule of thumb is wherever there's going to be water, there's going to be a GFCI. So when they trip, what they'll do is they'll break, see, GFCI receptacles will break the ungrounded, you know, hot and the grounded conductors, literally separating it. So you're allowing no more anything to occur on that line after its point of operation. Now a circuit breaker, which is back in your panel, will only break the one side, right? The ungrounded or hot conductors, pretty much stopping any deliverance of any kind of current at all. But the actual receptacle pretty much breaks all contact for anything past its point of operation. And kind of like, how would they do that? Well, two examples. And one, we have the circuit breaker, which is a GFCI circuit breaker installed. That means everything on this branch or everything on this line is protected by this GFCI. When we install it as a receptacle like this, basically the only thing being protected at this point is this receptacle. The whole branch here operates as normal, whereas just the GFCI circuit or just the receptacle itself is protected. Now there's a way to install these where you have the circuit after it, and then anything after it where the speeds would be protected as well. But in this particular diagram, the only thing being protected would be the receptacle itself, whereas the circuit breaker style will protect everything on that branch. So if we look at it, essentially here's your, so we have a ground fault circuit interrupter installed here as a breaker style. So it's going to protect everything on this line. Yeah, and they did, and believe it or not, this really you don't see an awful lot of GFCI circuit breakers. You see more of the receptacles more than anything. But I mean, they are available, and it is possible to go ahead and just install, you know, a GFCI breaker in your lines. Like if you wanted to feed everything in your kitchen with a GFCI circuit, it's allowable as long as you apply the right kind of thing to it, because certain things will cause a GFCI to trip that aren't true conditions per se. But essentially, this is how a GFCI works. If we look at, basically, we have a whole circuit set up here, right? Here's our breaker, feed through, or feeding in hot. We have a receptacle this way where it has a given load, which could be anything that's plugged into this particular device, right? So here's our hot, here's our neutral. And what it's looking at when they say this toroid coil, so it has like an electromagnetic coil inside, and both the hot and the neutral pass through it. And as long as there's a balance between the two, everything proceeds as normal. The time that it takes is when it sees the imbalance, like in this bottom part, it says, oh, there's a difference in, you know, a greater difference between what's being delivered and what's being returned. And then what it'll do is, based on what it senses because of that, it'll go ahead and, as long as it hits that range, it'll go ahead and trip that breaker or open the contacts of that device, so that way it's not delivering power any longer to this particular receptacle. So, and then so another point they make, well, because it used to be they would just install the GFCI receptacle and the receptacle would just protect itself. But these days, you can, they have two separate portions to them. One is where they have a wiring labeled line, and the other one's a labeled load. And so your incoming electricity would go to the line side as feeding the GFCI receptacle. And then you're able to have a load side, which means you could actually have a few other receptacles, normal ones, wired into this thing that would also be protected by the GFCI as well, which is kind of a standard practice these days. So if you were to go through and be installing a few receptacles on, let's say, your kitchen cabinet area or your kitchen countertop, so you could literally have one GFCI feeding like two regular receptacles and totally protecting them as well. So that way everything on your kitchen countertop is protected. Because on one given line, you cannot have more than one GFCI, whether it be the breaker or the receptacle style. They interfere with each other. So if I were to put in one GFCI feeding another one, and I tried to go live with both of them, what they'll do is they'll literally cause each other to trip. They'll sense that imbalance. They're both creating an imbalance with each other, and so they would actually trip.
I didn't Google that many of the answers. I was pretty confident that I knew how to do it.
And GFCIs have a manual test and a reset button, and these are set up and also supposed to be checked once a month for proper operation. So you'd go through and just hit the test and the reset button and make sure that the device does trip and reset as needed. I'm sure everybody does that. But here's a diagram illustrating what I was talking about. So here you have the beginning of the line being fed through, and you have the GFCI here. And it has a load and a line side. So the feed through goes through the line, and then the load would feed through the following receptacles. In this case, we have two other receptacles being fed by this GFCI. So that means they're protected by this GFCI. So anything were to happen on either of these outlets or receptacles would cause this GFCI to trip. And that's how you would wire that up in like a kitchen setting or even a bathroom setting where you had multiple receptacles on one line like that. But yeah, you would have the GFCI as basically as the first one in the line. And the back, it's very clearly labeled line and load. And like I say, line is where you're bringing the power in, and load feeds the following receptacles from it. And you can have this in a variety of ways. In this case, it's in the middle of the branch. So these first two devices here are not protected by the GFCI, right? But everything else after is. So these two devices are protected by this GFCI, and these two devices are not. So wherever this is installed in, if I wanted this to protect the whole line, he would have had to have been in the first place and then feed through everything after him. So wherever you install it as the line feed and then the load feed is where and what it's going to protect. Yep, and always be very careful to recognize which side is line and which side is load. So always remember, line is like power coming in and load is power being delivered. So, and they do, every one of them has a test and reset button. Some of them have little green LEDs on them, show that they're on. Some of them don't. So it's not a standard, if you will. But they should be tested fairly often. You should actually at least test them once a month. It wouldn't be a bad thing. Go through, test all your breakers in your panel once a month, test your lighting and everything. Nobody ever does this, but but yeah, there's and because the GFCI has electronics in it, and they can, and like anything, you know, stuff breaks down over time, and you could have that happen with your GFCI. It's something could occur as a failure, and it might be sitting there and looking like it's working right, but until the day of actual testing occurs, you wouldn't know. So it's always good to go through and hit your test and reset button just to make sure that that'll trip and come back on. So then we talk about the other one, the other big player on the block that's coming more and more popular, AFCI, which is the arc fault circuit interrupters. And here you see the circuit breaker style. And like I say, it is noticeably larger than a regular circuit breaker. And the same with the receptacle style. And again, and it's built very similar to the GFCI. But you notice it's stamped, so you'll know that it's AFCI instead of GFCI. So this is meant to feed things that are going to have extension cords involved and that regular cording, have devices hooked up to it like space heaters or vacuum cleaners and that kind of thing. But this would protect against, like I say, if anything were to occur with any of these accords. So really the way to look at an AFCI is like, am I going to have a cord and plugged into this thing running something? And if so, then an AFCI protecting it is probably not a bad idea. But that's really the way to look at it. AFCIs will be involved with corded devices. Anything with a cord that can be plugged in might not be a bad idea to have an AFCI on, especially if the cord's going to get a lot of traffic to it, like an extension cord or something like that, because you never know. You never know. But yeah, it's supposed to look for and sense arcing faults that could turn into fires. Like I say, you'll see these little electrical arcs dancing along, and that could be, you know, not enough to trip a normal breaker, but enough to start a fire. And you can get them these days that they're duals, where you have both AFCI and GFCI built into the same one. And the thing to remember here now is, what's the biggest factor that's keeping these from being installed everywhere is cost. These guys are a bit more expensive than your normal regular receptacles are going to be, or your regular circuit breakers. And again, it's going to come down to what's your customer going to want to pay, right? So the homeowner has to decide, well, do I want this installed at because of this price and stuff like that? So there is no actual requirements yet for AFCIs where it's considered these are a necessity like they do with the GFCIs, but it is something to consider when building or even renovating, upgrading a home or something. throwing AFCI protection into certain areas isn't a bad thing, especially heavy traffic areas where you're going to be doing a lot of, like I say, plugging and unplugging into a given receptacle for something. Then that one probably wouldn't be a bad idea to have AFCI protection on that. But any of the heavy dwelling areas, right? Family rooms, dining rooms, living rooms, parlors, so on, so on, and so on. Pretty much all through the house. We can look at these in different ways. They've got so many different styles. It's crazy. You could probably find anything and everything available that you could possibly want. They have combinations where you could feed both a branch and different feeder AFCIs and outlet AFCIs. You have branch feeders, which is a circuit breaker, okay? You have the outlet styles, where it's in a form of a receptacle, and they look a lot like GFCIs. They have the test and reset buttons on them. They're just labeled differently. And again, remember, these are active devices as well. They also have electronic components to them. So you do want to go through and test and reset them on a fairly regular basis to make sure that they're working right. And you can even buy them where it's like an attachment to your power cord. So you could basically on like your vacuum cleaner or something, and you would basically have this thing plugged in on the end of it, and then that would plug into the wall. But in this day and age, for AFCIs, the most common types they use out there is a full circuit breaker style. Compared to the GFCIs, where the most common circuit type used are the receptacle styles. Anyway. And they got some other ones out there these days. I'm going to take a look at like little other special purpose receptacles, if you will. And these days they're coming out more and more with the tamper resistant style. And what that means is it'll have like, this picture doesn't do it justice, but across the cover of these, there's actually like little nylon guards that'll sit there. So like, let's say your 2-year-old's running around and he's at that age where he's poking stuff into places, right? Well, what this does is basically the nylon thing won't break away unless there's pressure applied on both sides. So if your little 2-year-old comes by and he's trying to poke his toy into one side or the other one, well, if both sides aren't being hit, that little nylon shield thing, it won't peel away. It'll stay blocked. So the way these things are set up is you have to basically apply pressure with the dual plug and be hitting both sides of it, and then that little nylon shield there will slide back and allow you to plug it in. But that one's becoming more popular, just to keep for kids from getting into stuff they're not supposed to. And then they got these weather resistant ones, which are, I don't want to call them, they're not water resistant. Nothing electrical is going to be water resistant per se, or waterproof. But they're weather resistant, so meaning they hold up better in damp locations, so they won't corrode as easily. They've got like special material and coatings on them so that the insides won't get corroded and that kind of thing and break away. Because you really can't see in the inside of these things whether everything's being held up well or not. One day it's like, oh, that receptacle's not working anymore. Yeah, well, your contacts are probably old and given out. They're all like spring loaded. And anyway.
Tom,
Yep.
what the hell is that shit?
What's that?
What is making all that noise?
Puppies.
Oh, Jesus Christ. Okay.
That is a little gaggle of puppies. Yeah, my wife likes to breed dogs. And this is our latest batch.
I was
I'm not happy right now. Why, you
Yeah.
want a puppy?
No. After doing that, no thanks. I was wondering if someone was beating a dog or something.
No, I wish. No. Anyway. But NEC is pretty specific. and what type of receptacles are permitted for replacements. So again, if the device is already there, it's grandfathered in, right? But now your receptacle is not working right anymore. You're going to replace it. Double check. Make sure you got the right kind of receptacle that's going to go in that spot. Maybe the one that was in there was fine back in 1975, but it ain't so fine today. You might have to take some special considerations. Well, and anything you might want to find would be in this section, right? 406, paragraph 4, section D would have information on that and tell you what types of receptacles would be permitted for use, for replacements, depending on your situation, especially if it's older style wiring. Because if you had a situation where grounding doesn't exist, there's always special things that we have to take into consideration with that. Because they're still out there. You get the old 2-wire receptacle styles that don't have a ground plug to them or anything like that. And it's like, oh, we got to replace it. What do we do? And this would cover all specifications for that, what you might have to consider. So, but yeah, I think pretty much, there's the old 2-wire style, right? No ground plug to them. And then if you needed to replace it, right, here's where, as long as you had an ability to make a ground or have a ground come in, then we can go with this. But otherwise, if it does not have a ground wire available to it, then you have to go with something else, because it would have to actually be labeled that it does not have a ground. Or you could bring a ground in. There's a few things to be considered with this, a few things you would have to go through. You can't go back and go to the 2-wire style. You just simply can't buy them anymore. So you would have to install these types, and to do it properly, it would have to have a ground to it, but you can go through, tighten down the ground screw and label it, no ground into it, and it would literally be ungrounded. GFCI and that kind of thing might not work properly on it. There's different things, different considerations you would have to go through. But anyway, the book also this chapter goes through and talks a little bit about surge protection. Now, believe it or not, you can buy receptacles that have built-in surge protectors with them. They look kind of weird. They're these blue guys like this, and they'll look like an AFCI and look like a GFCI, but they're really not. They got a little turnable thing to them to tune them, if you will, to set them to the rating that you want them to be. Usually what most people have for like their computers and stuff like that are these power strips. But you can buy a receptacle style. They are available. It all depends on what you want, what's convenient. And these are all things that could have arcs in your home. Like I say, the more toys we have, the more problems we can build up. People these days, they have fitness equipment in their house where we got the treadmills and stuff like that, but still got the old vacuum cleaners, our lights, whether you're a do-it-yourselfer, you got your own power equipment going on. You got fancy lights going through with motors on them and that kind of thing. These all can, all these little toys can all create, what they call operational arcs. And what does that mean? So that, well, anything with like a motor like these and stuff like that, when they're first turned on, they're going to draw a lot more current than they normally use to operate. So you can't have a breaker be so sensitive that it's going to trip every time, because you'll never get anything done. So they give it a X amount of time, and then it'll go through and trip. And that's considered just operational. But then if you have something where, yeah, no, I'm sorry. Welcome to the land of puppies. But there's an AFCI, and you can see it has an actual active circuit board to it built in. Still has the traditional style electromechanical operation. There's normal, a normal circuit breaker, but then we have this whole extra set. Like I say, they have an extra wire built into it where you literally run the neutral to this thing. Where a normal circuit breaker, you generally only have the one wire running to it. But in this case, you would have the hot running to it, and you would also have a neutral wire running to the panel. So you would have to have a lot more neutral bus bars available because you would actually be populating them quite a bit with this device. Oh, but that's pretty much it. And I mean, really, you look at your two main things out of this chapter is the GFCIs and the AFCIs, and then looking at surge protection. I mean, surge protection is just protecting your electronics or any of your sensitive equipment. I don't think you would want surge protector on like a blender or something like that, but on your TV or smartphone plugins and things like that isn't a bad idea. But I'll stop sharing that. And then, like I say, where am I at here? I'll assign, our homeworks are going to start getting to be a little less and less. I'm sure everybody will be very sad.
Hey, Tom. Speaking
Yes.
of homework, I didn't get to chapter 6. I didn't realize it was due today. So can you open that back up?
Oh, you guys. Chapter, oh yeah, it was, huh? All right. We'll extend it to tomorrow. Yeah, I showed you guys. Let's see. Yeah, I'm gonna post the next chapter homework today, but I don't think I have any worksheets or anything. Double check here.
All right. See you later.
All right. I'm pretty sure for today. Yeah, I'll just be posting chapter 7 homework. I don't have any worksheets or anything. Really, I want everybody to focus on getting those, getting your service entrance calculations all done. And then if you have any questions on that, let me know. But hopefully that example will show you. Like I say, the most important thing is getting that, getting your square footage down. And look at that and look at sheet number 4. It does list out like all the special instructions you might have. And just go one at a time. Oh, Jesus. Hey. Oops. Anyway, my wife's going to work. So. But yeah, just follow the square footage, and then, like I say, the special instruction sets for all that after. Should go through. It should be fairly self-explanatory. And like I say, if you're off on your square footage, I'm not going to kill you for it as long as you do your math right. Come up with the right service size based on your calculations, what your different conductor sizes are going to be, and what size that raceway is going to be, because that's like mega important as far as this goes. Because really that sets up all your equipment, getting everything laid in to get your service installed, right? So that way you now have power to your house and properly. So, and this is what every contractor would go through if they were to figure out, you know, really all they get is, you figure they get a set of prints for making a job bid, and they'll review the prints based on, you know, doing a worksheet very similar to this. Most companies will have something like this laid out, And then they would just go through and decide what factors would need to be in place for this. And then that way they can go ahead and make a materials list with labor, and then make a job bid up based on that. And this is really what they do. And after a while, I mean, you know, if you do anything long enough, you don't really need a worksheet anymore. You just know what to do, right? But this is to get everybody, make sure you follow all the steps and don't miss anything, and get your house sized properly. And then you know for sure whether you got the right size service or not for your thing. And you can even go through and look at your current house and make sure that they did it right. Because you could even go through and calculate through and based on, you know, your square footage size and stuff like that. But, you know, and again, I mean, it depends on when your house was built and when the service was installed and stuff like that. But you can compare and see, is it up to snuff or current standards or not? That's if you were really bored and wanted to go through it, but no. But that's all I really have for you guys. Like I said, there's no articles or anything. I'll post the chapter 7 homework. We'll have posted today. And other than that, that's really it. I mean, we'll go through, and then on Wednesday we'll talk about chapter 7. And now we're just pretty much progressing through. I will have 2 more uglies quizzes coming up, and then I think I gotta look and see when I have our next quiz. But other than that, that's really all I have for today. Anybody have any questions, or we're doing okay? Hopefully I got my Zoom thing all worked out and everybody can get logged in when they need to.
So you still, that phone number is still right on there? Because I've tried calling to ask questions and
My home number? Well, it all depends on if I'm home.
okay.
I can't promise. I don't carry the thing around with me, but yeah, that is my correct number.
All right.
I mean, I apologize. I know. Let's see. But no, yeah, that is definitely my my home number. But yeah, if it doesn't go through or hits the answer machine, and all I could say is like leave me a message, and I get back in the house, and I promise I will call you. But oh, he left me. All right, well, I'm gonna quit recording.